welcome to this introductory presentation on streams and rivers in Florida, the dynamics of flowing water. This is the first in a series of presentations that will focus on the physical, chemical, and biological structure of streams. We'll introduce various principles of stream and watershed ecology that we hope will deepen your understanding and appreciation of these systems. This series will be broken down into several modules with one or more presentations per module. Each video will build upon materials covered in previous presentations, and throughout we'll encourage you to apply the concepts via questions, quizzes, and scenarios. Module 1 will introduce basic concepts and vocabulary related to hydrology and stream ecology. Module 2 will discuss elements of proper sampling design that will put into practice many of the principles from Module 1. Module 3 will discuss and demonstrate various techniques used in Florida's Stream Bioassessment Program. And finally, Module 4 will discuss how to interpret the results of the data you and others collect and what it means about the health of these systems. So to begin, it's helpful by defining what a stream is. William Beck, one of the early aquatic ecologists in Florida, defined streams as a body of water with unidirectional flow of measurable velocity. And from this definition, we can exclude several water body types. For example, tidal creeks. They don't meet the unidirectional flow portion of the definition because their flow changes with incoming and outgoing tides. It also excludes ponds, lakes, and wetlands which lack measurable velocity under typical conditions. A slight refinement to this definition adds that streams transport sediments. This is an important but overlooked aspect of stream function. In this aerial photograph of the Blackwater River in the Florida Panhandle, we can see a large sand deposit that's resulted from materials being eroded from further upstream. When a stream is functioning properly, it's in a state of dynamic equilibrium between erosion and deposition. And when this equilibrium is not maintained, streams develop characteristic patterns that can be observed and measured. At this point, it would be helpful to define a few key terms. The large deposit of sand we just saw in the previous slide is referred to as a point bar. A point bar is a large deposit of alluvium at the inside bend of a river. This brings us to our next term, alluvium. Alluvium comes from the Latin word meaning to wash against, and refers to loose, unconsolidated sediment that's been eroded, reshaped, and redeposited by flowing water. And now that we've defined a few terms, let's discuss stream classification and why we would want to classify streams. Well, there are many reasons, and here are just a few. It allows us to predict a river's behavior from its appearance. We're better able to understand the interplay between sediment transport and deposition. We can extrapolate our expectations to streams of similar types and develop expectations for the biological communities that are associated with the different stream types. The Florida Natural Areas Inventory, FNA, developed a simple system for classifying Florida streams into 4 major types: alluvial, sometimes referred to as wash-load or continental, blackwater, spring-fed, and seepage. Alluvial, if you notice, is similar to the word alluvium that we just defined, and it gives us a clue about the nature of these systems, in that they carry large amounts of sediments, often resulting in higher turbidity or suspended solids in the water column. And for this reason, these systems are sometimes referred to as wash load. These systems are sparsely distributed in Florida and are generally restricted to the Florida Panhandle. And because they originate in states to the north of Florida, they're often referred to as continental rivers. Examples include the Escambia, Choctawhatchee, Apalachicola, and Ochlockonee. In this photograph of the Choctawhatchee River, you can see it has a slightly muddy appearance, and this is the result of the alluvium that's being carried downstream. Blackwater streams and rivers typically drain extensive low-lying wetlands. Then this results in the water being a dark stained color from the decomposing plant materials in the surrounding watershed. These are the most common stream types in the southeastern coastal plains. Examples include the Ocilla, Sopchoppy, St. Mary's, and Peace rivers. In this photograph of the St. Mary's River, you can see that the water is clear, but it has a dark color to it from those tannins leaching out from the surrounding wetlands. Perhaps the most well-known systems in Florida, spring-fed rivers. They derive most, if not all, of their water from deep aquifers in areas where limestone is close to the surface. The water is typically clear due to the filtering action of the soils that the water percolates through. Examples include the Rainbow, Wakulla, Alexander, and Silver. And perhaps the least known of the stream types identified by FNA are seepage streams. And unlike spring-fed systems that derive their water from the deep aquifer, seepage streams derive their water from shallow superficial aquifers. But still, the water is filtered through deep sand deposits and thus is typically clear. These systems often form the headwaters of many alluvial and blackwater streams. Examples include Goldhead Branch, Alaqua Creek, and Little Alaqua Creek. This photograph, taken in Goldhead Branch State Park, has the characteristic clear water and small size that's typical of these systems. Another common way to characterize streams is by their size, and the most common method for classifying streams according to size is the Strahler classification system. This system assigns the smallest streams to a first order, and when two streams of the same order come together, then they are assigned to the next highest order. For example, if you have two first-order streams coming together, they form a second order. And only when you have these two streams of the same order coming together do you get the next highest order. And first through third order streams are typically considered headwater streams. And fourth through sixth are medium-sized or wadable systems, and seventh and higher typically constitute what we think of as rivers, although that term is sometimes used less formally to refer to larger bodies of flowing water in general. So, what is the longest river entirely within Florida? If you said the St. Johns River, you are correct. The St. Johns River, highlighted in yellow, is a seventh-order river. It's over 300 miles long and winds through 12 counties. Well, until next time, whether you're working or playing in Florida's flowing systems, we hope this information will add to your understanding and appreciation of these unique systems.